Okay, next we will verify this design controller in Plex. First we will do it in the frequency domain. Okay? So first of all, I enter the controller using this transfer function block in Plex, and if you see what is inside that, so this is the numerator corresponds to the zeros. So I have this entered Kc, and recall that I defined Kc in my initialization, and I also defined omega z and omega p to the values that I got from MathCAD. Let me just show that quickly. Simulation parameters, initialization, and here are the Kc values, omega z and omega p, exactly what we got from MathCAD. So this has the numerator coefficients. So the constant Kc multiplies both of these, and the coefficient of the S term is 1 over omega z. The constant term is 1. And on the denominator, I do this slightly differently. I have the 1 over S term as a separate integrator, and I only put the pole of my controller in this transfer function. So that would be 1 plus S over omega p, and so the coefficient of S is 1 over omega p, and the constant is 1. Okay? And then here is my integrator. So now I can go ahead and remove my this constant and connect the controller output to my PWM block. Okay? So that is done here. Right. So there are a few things that I want to verify and validate and demonstrate. First is this feature of this loop gain meter. Okay? So I showed where you can get the loop gain meter from the library. So this needs to be run in closed loop, and this will give you the complete loop gain. There are several criteria that you need to meet on where to place this perturbation. But for most DC-DC converters, if you want the loop gain, one of the best places to put the perturbation is in the place where you actually sense the output voltage. So output voltage is measured here, and that is sensed and fed here, and in that path you break that and insert your loop gain meter. Okay. So VO comes from here, and then I have the loop gain meter, and its output goes to this block where I'm doing the difference between the reference and the output voltage. Okay. So whenever I do the small signal analysis, I can only select which perturbation and which response I am interested in, and when I do that, the other perturbations do not affect anything. So I can still retain all the other perturbations. They don't really impact my loop gain measurement. So that is done here. Let me go ahead and do the small signal analysis. Okay, so now I want to select the impulse response again, and the system period, frequency range, amplitude, they're all same as before. The difference here is instead of d tilde, I select the loop gain meter as my perturbation. The response is also loop gain meter response. Okay, so this gives me directly the loop gain. So do a start analysis. Okay, so that is the complete loop gain that includes the planned transfer function as well as the designed type 2 controller. Okay. So what are the two things that we need to check? One is the magnitude. In the magnitude plot, does the crossover, that is the 0 dB point, is it exactly at 10 kilohertz? So once again, if I in my cursor type in 10,000 here and look at the magnitude plot, it is like minus 0.008, so that's very close to being the 0 dB or magnitude of 1, so that matches very well. The second one is under the same frequency, 10 kilohertz. Look at the phase plot, and we expect that to be minus 120 degrees. Plex plots it, so the minus 120 is actually plotted as minus 120 plus 360. So that's 240 degrees. So that also matches correctly. Another important information that we can verify on the loop gain plot is that at low frequencies, so I plotted only from 10 Hertz, so even at that frequency, the gain is more than 65 dB, so that's more than a factor of 1,000. And when I go to 1, it's going to be another order of magnitude higher, and so on. So the DC gain would reach infinity if we can go all the way up to 0. So this will result in a 0 steady state error. I should also mention that the meaning of using loop gain perturbation and loop gain response in our impulse response analysis is so we are actually looking at the gain from applying the perturbation at this end of the loop gain meter, go around the entire loop through the controller, through the plant, up to the output voltage that is being sensed, all the way up to this sensed feedback point. So this is where I measure the response. So that is why it gives us the complete loop gain. Another thing that I want to emphasize is that in Plex, it's important when we do this small signal analysis, whether you want simple transfer functions from one point to another, or you want the complete loop gain or closed loop gain that we're going to see next. It is important to give the correct initial conditions. So I did give the initial condition for the capacitor output voltage to be 12 volts, and since I'm simulating for a nominal current of 3 amperes, that is my inductor current as well, initial inductor current. And the other really important initial condition to give is the output of the controller. Okay? So that is the main reason why I implemented the controller as a separate transfer function accounting for the 0 and the pole, and another integrator in series with that. So in the integrator I can give the appropriate initial condition. So in steady state we know that the D has to be VO over Vin, and for this operating condition it is 12 over Vin of 25 volts. So that's the initial condition, and I also give limits on the duty ratio. It can actually go from 0 to 1, but I'm limiting to 0.1 to 0.9. You can also give 0 to 1. There will not be any change in the small signal analysis result. Okay, so the next thing that I want to show in Plex is the what we looked at so far is the open loop gain or the loop gain. They are synonymous. I want to next show the closed loop gain. Okay? So you can actually calculate that as GOL or 1 plus GOL for unity feedback system, but you can actually get that directly from the switch model simulation. So the block that the perturbation and the response that does that is you perturb the V reference itself. For by definition, the closed loop gain GCL is VO divided by the VO reference. So I perturb directly the VO reference. So this constant is really my VO reference, which I defined as 12 volts, and I perturb that reference input, and once again measure the output voltage through this response block. So that will give me the transfer function from VO reference to VO output, and that by definition is the closed loop gain for this output voltage control system. So once again go to simulation analysis tools and select impulse response, and the perturbations and response I'm going to select. Perturbation is as you can see in the schematic, it is V reference tilde, and the response is same as the output voltage, which is just simply called as response right here. Okay. So let's do the analysis. It is right here. Okay, so that is the closed loop gain. So does it make sense? We know that we have studied in previous videos that the closed loop gain is it's exactly 1 whenever the open loop gain is very high. So as an approximation, close to the crossover frequency, the closed loop gain should be unity or 0 dB, and that's exactly what we get at low frequencies. The bandwidth is around 10 kilohertz, so till up to at least about 2 kilohertz, it's close to 0 dB. then it has some small variation. Notice that the scale is it's just 2 dB, so this just increases just about 2 dB. And after crossover frequency, actually well after the crossover frequency, the closed loop gain simply follows the open loop gain. Actually, I'm going to plot the this closed loop gain simultaneously with the open loop gain and show that this really in this frequency range it follows the open loop gain. The lower plot of course is the phase plot of the closed loop gain, and once again for frequencies well below the bandwidth of the crossover frequency, it's 10 kilohertz, well below that the phase angle is simply 0 degrees. Okay. So up to I would say about 2 kilohertz or even 3 kilohertz, this controller is an ideal controller, signifying whatever VO reference we give, we get the same thing at the output, okay, under those frequencies. Okay, so let me go ahead and draw the closed loop and the open loop gain on the same plot. So in order to do that, if you go back to my analysis tools, what I have at the end is the closed loop gain. So let me go ahead and save this this plot. Okay, so that is done. And to get the loop gain, I need to do perturbation of the D. So this is actually the loop gain is obtained from the loop gain perturbation, and the response is the loop gain meter response. So let's redo that again, start analysis, and what you get are the two plots. So let me make this also bigger and give it a different color, maybe. Okay. All right. So obviously the top one should be the open loop gain or the loop gain, and the bottom one is the closed loop gain, which is 0 dB for much of the frequencies below the crossover frequency. And you can clearly see that after the crossover frequency, the two gains they just match. Okay, so after the crossover frequency, GCL just follows GOL. A similar thing should happen on the phase plot, but because Plex adds this 360 degrees to this open loop gain, they look different. But at frequencies well above the crossover frequencies, these two phase angles should match. Okay, the next thing that I want to do is show the effect of closed loop control on the output impedance. So the changes in the load is a disturbance to the system, and we want the transfer function from the load disturbance to the output voltage to be as small as possible in as large a frequency range as possible. So especially if you're interested or if your application has very fast and large step load changes, and if your output voltage is constrained to remain within a very tight narrow band, then the output impedance, the closed loop output impedance, is a very important parameter. So what I'm going to do is I'm going to obtain this output impedance, which is nothing but the impact of output current perturbation on the output voltage. And I'm going to do that under two conditions. One is open loop. So I do that by removing this feedback connection and then connecting back my kind of constant D, but with my just constant D. So this D perturbation, when I am studying the IO perturbation, this does not affect anything. So I can just leave it as it is, or I can delete it and connect D directly here. But what I'm going to show is perturb the current and look at the response at the output voltage. But here there is no closed loop control because I've removed that path. So let's go to the small signal analysis tools, impulse response. Again, the first three parameters are the same, but the perturbation now is IO tilde. That is the load current perturbation, and the response is once again in the output voltage. So I have the response block connected to the output. So let's start analysis, and what you get, okay, so I should have removed all the earlier plots. So let's go to view traces and remove all of these. Okay. Come back to my start analysis here, and what I have, this is the output impedance, or V tilde over I tilde transfer function, and for this particular system it is always less than, at least always less than 0 dB, so it does not amplify the load current perturbation, and it has reasonably low gain values at low frequencies, but becomes higher as you go to higher frequencies. And as I mentioned, ideally we want this to be extremely small. Okay? So let's see how the closed loop improves upon this, and in order to compare the two, let me save this plot. Okay? So the next I will plot the output impedance with closed loop and see how the two compare. So to do that, I go back to my schematic, connect back my closed loop controller. So the control signal for the PWM block would be from the output of the type 2 controller, and go back to small signal analysis and do the same perturbation and same response. Okay, so it's same I tilde, same response at the output, but the difference is now this is with closed loop control. Okay. So do start analysis, and so you have now two plots. This one, let me make it bigger. And could be in some other color, and this also is bigger. Okay, so the green plot is what I plotted originally. That was the output impedance under open loop control, and the red or brown is same output impedance under closed loop control. So you can see that under low frequencies it will become even larger when you go to even lower frequencies. Even for 10 Hertz there is at least a 60 dB or a factor of 1000 reduction in the output impedance. So the closed loop gives you a much better response to step load changes, meaning the output voltage would deviate significantly by a smaller amount. But the closed loop control can help only up to the bandwidth. Beyond the bandwidth of the crossover frequency, you can see the open loop output impedance and the closed loop output impedance kind of merge, and there is no further improvement. And the last thing that I want to demonstrate is the other disturbance transfer function. This time it is from the input voltage perturbation to the output voltage. So to perturb the input, I actually connect a controlled voltage source in series with the input DC voltage, and the control input for that is the V in perturbation, and AC perturbation, call that as V in tilde. So this is another perturbation block, small signal perturbation block, we call it as V in tilde. And I would see the propagation of this disturbance to the output voltage and measure it by this response block here. Once again, my objective is to do this for both the open loop control case and the closed loop control case. I'll start with the open loop, so I've connected this constant D to the input of the PWM block. So go to small signal analysis, impulse response, and this time my input perturbation is V in tilde, and the response is once again at the output, so that is the same as before. Okay, so this is what is the this is the input voltage to the output voltage transfer function, sometimes called as the audio susceptibility transfer function. So this is with open loop. Once again, this being a disturbance transfer function, we want the magnitude to be as small as possible over a wide frequency range. So let's see what effect the closed loop has. So let me connect back my controller output to the PWM block and then do the same perturbation and analysis. So the perturbation response, they do not change. Only change is made in the schematics connecting the closed loop controller. I should have saved this, so let me save that and start analysis for the new case. Okay. So now I can so here the upper plot, the green plot, that is what we got under the open loop control condition, and the red corresponds to the closed loop condition, and that once again it is the transfer function from input voltage disturbance to the output. Clearly see again about a 60 dB increase or 60 dB improvement in the audio susceptibility transfer function. So it means that if there is some perturbation, one practical example is perturbation at the line frequency or twice the line frequency, like 60 Hertz or 120 Hertz, when your input is derived from a rectified AC, line frequency AC. Then your output voltage should attenuate this 120 Hertz ripple as much as possible. So that's where this transfer function becomes important, and you want an extremely low value at those frequencies. Okay, so 100 Hertz is here, so you want somewhere in this frequency range the gain to be small, and you can see that the closed loop improves that performance by about 40 dB or so. And as before with the output impedance case, beyond the crossover frequency, the closed loop controller cannot do much. The two disturbance transfer functions merge after the crossover frequency.